guys. So today we're going to look at applications of exponential equations. So we're going to use logs to solve these equations, but really the setup is really going to look like a lot of exponential equations. There are two main applications we're going to look at. One of them is interest with money, and the other is half-life and doubling, which will be kind of similar to some of your science classes. So the first thing we're going to look at is interest compounding. So you probably saw this in Algebra 2, but in case you don't actually know what it means for interest to compound, I'm going to show you guys kind of an example. Okay, let's say you have $100 and you get 10% interest on that. All right, if your interest were to be compounded yearly, what that means is after 1 year, so you have year one, you start with $100. You would get 10% interest, so you would then have $110. Well, year two, you're still going to get 10% interest, but now you have $110, which means you're actually going to get $11 interest that year, so you have $121. So then year three, when that starts, you'll have $121. You'll add your 10% interest, which is again now an additional dollar, and you end up with $132 or $133.10. So as your interest compounds, you're able to get interest on that interest. So compounding interest is a good thing if you're gaining money. It's a bad thing if you're paying it on something like a credit card or a loan. So let's see what happens if interest were to be compounded quarterly. So if it were compounded quarterly, that would mean at the end of the first quarter. So at the end of the first 3 months of the year. Let's say it's the same situation. It's $100. You're going to get a fourth of that interest after the first quarter. So the first, that starts with $10, that's a year's interest, but we're only going to get a fourth of it. So when I add that in, I have $102 at 50 cents at the end of 3 months. Well, now quarter two, I'm going to start with that 102.5, and now I'm going to get 10% of that, which is going to be $10.25. It's still divided by 4 because we're just looking at the 1 quarter of the year. And then we'll move on to the third quarter, which is about, halfway. We're past the halfway point of the year now. We're going to take that $105. We'll get our 10% of that, which is $10.51. Only a quarter of the interest, because again, we're just looking at a quarter of the year. Add those together, we're at $107.69. Then we'll look at the end of the fourth quarter. So at this point, we've accumulated $107.69. I'll get our 1 quarter of interest, which is $10.77, only the quarter of it. Add that together and we get $110.38. Now, the end of the fourth quarter, that is the end of year one. So you'll notice when interest was compounded quarterly, you ended up with more money than if your interest was not. Now, I know it's not a huge difference. However, if you have a high interest rate, a lot of money in a long period of time, it could make at least a noticeable difference. So it is something important for you to pay attention to. It also, again, this works both ways, not just with gaining money, it also works with paying interest on something like a loan or a credit card. So keep in mind, interest compounding does make a difference. So when we talk about interest compounding, we're going to look at 2 equations. The majority of our cases are going to use this first equation, and that is depending on if your interest compounds at almost any rate, okay? When we use that equation, P is the principal, which is the starting amount. R is your rate. You always write your rate as a decimal. Okay, you always write your rate as a decimal. So like if it's 5%, you would put 0.05. T is the time in years. It has to be in years. And N is the number of times it's compounded in 1 year. So if it's compounded monthly, N is 12. If it's compounded quarterly, N is 4. If it's compounded daily, N is 365. So those are the different things that N could be. A is the amount you have after however much time you use in your equation. Now, there's a special type of compounding that you probably looked at last year, and that is continuously compounding interest. So continuously compounding interest has a different formula. You will specifically see the phrase continuously compounded if you use this formula. If you see any other type of compounding, you're going to use the first formula. So this formula we call the Pert Formula. P is still the principal or the starting amount. E is the E that's on your calculator. Okay, it stands for about 2.718. R is still your rate as a decimal, and T is still time in years. So let's look at a couple examples here and plug these values into our equation. An account pays 3% annual interest compounded monthly. So that is our clue that we are going to use the first equation because it does not use the phrase continuously. We're going to deposit $5,000 in that account. How much money will I have after? We'll start with 18 months. So 18 months. So we don't know the amount of money. We do know the principal. The principal is the starting amount, which is $5,000. 1 plus the rate, and we write the rate as a decimal. So 3% is 0.03. Divided by the number of times it's compounded. If it's monthly, that's 12 times a year. That same N is in the top, and T is time. So if it's 18 months, we have to write that as years. 18 months is 1.5 years. At this point, you can just plug all of this straight into the calculator, just the way that it's listed, and you will get an answer of $5,229.85. All right, if you want to find out the amount of money you'll have after 3 years, it is the exact same equation. The only thing that's going to change is that one number that's in the exponent. So the other values are the same, but this is now going to be 3 times 12. Again, at this point, the variable that you're looking for is already by itself. These are the equations that we like. These are the easiest ones to solve because it doesn't really require any algebra. At this point, we can just type this into our calculator and we'll get our answer. So after 3 years, I would get $5,470.26. If you wanted to do 10 years, you would do the exact same thing. But again, instead of 3, you would use 10. So if I do 10 and 10, plug those in, and I'll have $6,746.77. All right, let's look at this next one. After how many years will you have $10,000? So this one's going to require a little bit of algebra. So we do know the A value now. Our A value is 10,000. Our starting amount is 5,000. I do still know the interest rate. I do still know how often it's compounded. What I don't know now is the time. So my variable is in the exponent. If your variable is in the exponent, then what you have is an exponential equation. So we're going to solve this like we did a few days ago. So what I have here, this 1 plus 0.03 over 12, that is the base. Now keep in mind that actually is a number. You can plug that part into a calculator and you can simplify that if you want to. So this is 5,000 times, if I plug in 1 plus 0.03 divided by 12, then I'm going to get 1.0025. So now I need to solve this exponential equation. So if you remember, to solve the exponential equation, get the exponent and it's the base of the exponent and the exponent by itself. So I'm going to divide by 5,000. And once you have the exponent by itself, then you rewrite it in in log form. So it's currently in exponential form. Now we're going to write it in log form. So this would be log base 1.0025 of 2 equals 12x. So that's the log form from the exponential form. So this is exponential form. This is log form. Then at this point you have one last step. You would divide both sides by 12. Now what you have here, this is your exact answer. This is your calculator ready answer. Since this is an application though, we do want to know what that actually is. So we're going to go ahead and actually type this into a calculator and round our answer to the nearest hundredth. Now keep in mind when we actually solve this, what we're doing here. Okay, when we actually solve this, we're going to have to do log AB in order to get that log base on our calculator. So plug this into a calculator and you'll end up with 23.13 years. All right, let's look at a few more. So this time we have $5,000 to invest. in an account that earns 1.75% annual interest. This time we see the phrase compounded continuously. That is our clue that we're going to use the Pert formula. So how much money will you have in 10 years? So amount we don't know, 5,000 is the start. E is E, 0.0175. Again, we write it as a decimal. Move that over 2 places. And then times 10 because that's my time. This one's an easy one to plug into your calculator because the variable is already by itself. Plug it in and I get 5,956.23. All right, now, when will you have 7,000? So this time the 7,000 is the amount, 5,000 is the start, the rate is the same, but we don't know time. That's my x. So again, we're going to have to solve this the way that we have solved these questions algebraically. So get the exponent and the base by itself. So divide by 5,000. And then at this point, we can rewrite this as a log. So this would be log base E of 7 over 5 equals 0.0175x. Now remember, log base E is the same thing as ln. Now to get x by itself, we'll divide by 0.0175. So this is my calculator-ready exact answer. Since we have a calculator, let's go ahead and also find the decimal. So at this point, we can plug this in, and I'm going to end up with 19.27 years. All right, we'll do one more financial one, and then we'll move on to half-life and doubling. If you feel comfortable, pause the video, try this one on your own. All right, 2 accounts. Account C pays 1.65% annual interest, compounded continuously. So we're going to use PERT. So A equals 10,000 E to the 0.0165. And our question is asking when it will have, how much money it will have after 5 years. So times 5. Account Q, compounded quarterly. So we're going to use the other formula. So again, 10,000 is the principal. 1 plus 0.0168. Compounded quarterly would be 4 times a year. So our n is 4. And again, we know that our x is 5. So at this point, we just want to figure out which one's going to have more. So your variable's already by itself. Plug it in. I get 10,859.99 for account C. And I get 10,874.38 for account Q. So you can see we're going to get more money out of account Q. So even though it's not, the interest is not compounded as often, the higher interest rate does make a bigger deal. So I'm having trouble spelling the word account, and my letters are all blending together. All right, so the last application we're going to look at is half-life and double life. So this is something you may have seen in chemistry. You also may have seen this in algebra 2. So this is our half-life equation. The double equation, if you notice, it looks the exact same, except instead of 1/2, you have a 2. So what this is, A with that little sub-zero is your initial amount, very similar to the principal, okay, the starting amount. The number by itself, the A sub t, that's the amount you have after whatever time that you're using. Again, very similar to the equation we just had. T is our time, and our time does not have to be years this time. But whatever time you use there, it needs to be consistent with the time you use for that variable. And it needs to be consistent throughout the problem. So just keep that time consistent. So your H, or your H there, is the half-life or the amount of time it takes to double. Okay, so that will actually plug in. So let's go ahead and fill this in. The half-life of a radioactive element is 40 days. We start with 200 grams. How many grams will we have after 100 days? So we don't know how many grams we have after that time. We do know the starting amount. We're talking about half-life, so we're using 1/2. The half-life is 40. And then the time here, oops, sorry, I went backwards. My time is 100. My half-life is 40. That's my equation. My variable is already by itself. At this point, I can go ahead and just plug this straight into a calculator, and I get 35.36 grams. All right, let's look at same situation, different place for the variable. How long would it take for 15 grams to remain? So we want AT to be 15. We're still starting with 200. We're still looking at half-life. We don't know time. We do know the half-life is 40. So again, just like in the previous questions, get the exponent and its base by itself. So divide by 200. So if I divide by 200, that would give me 3 over 40. At this point, the exponent base is by itself. So now we can rewrite this. This is exponential form. Let's write it in log form. Log base 1/2 of 3 over 40 equals x over 40. Then your last step to get x by itself would be to multiply both sides by 40. And that is your exact calculator ready answer. Since we have a calculator, let's go ahead and plug it in. Remember to use log AB in order to get that base. Plug this in and we end up with 1,400, oh, so not 1,400, 149.5 days. So again, your time here was consistent for the whole thing. Okay, we were looking at 40 days for the half-life, so my answer is in terms of days. So keep that time consistent. All right, last one. Let's look at doubling. Okay, very similar situation. Really, the only difference here is we have a 2 instead of a 1/2. So the number of bacteria in a culture double every 5 hours. It initially has 3 bacteria. So how many bacteria would there be after 1 day? So again, we don't know how much. That's our variable. We know our starting amount. There are 3. We know it's doubling. It's doubling every 5 hours. And then we need 1 day in terms of hours. So we're going to use 24. Because again, the time has to be consistent. Variables by itself, plug it into a calculator, and we get 83.57 bacteria. Now I'm going to go ahead and round this up just because we're not really going to have a half a bacteria. So I'll say that there's 84. All right, again, same situation, just the variable's in a different place. How long, so we don't know time, that's my variable, will there be 1,500? So 1,500 is equal to 3 times 2 to the x over 5. If you feel comfortable, pause the video, try and solve this one on your own. All right, again, get the base by itself. So to get the base by itself, you'll divide by 3. The exponent base is by itself, so write this in log form. Log base 2 of 500 equals x over 5. Multiply both sides by 5. And then you have your exact answer. Plug this into a calculator, use log AB, and you'll get 44.83 hours. Again, time is consistent, so it was hours at the beginning. We ended with hours here. All right, guys, so that is it for applications. Again, this is also some solving practice. And that's all. You guys have a good day.